System, this is a free game.
I got my money's worth out of this. Yeah, screw that. Still getting my money's worth out of that.
How is everyone's spring break? We don't really have a spring break. Okay, two announcements. First, paper report due is today, and assignment 1 has been posted. We have 10 days to finish the assignment. So basically, it's probably due for in-class exercise 102, 1 and 2, and this is it. So you're going to read it with your book number. So, yeah.
If we're presenting, we don't need to turn anything in for the paper or anything, right?
Yeah, that's right.
So
So, last class, we went through some basic knowledge of malicious code or malware. We talked about different types of malware out there and how those adversaries and criminals they actually make money from malware. And we looked a little bit at how to do reverse engineering. We looked at this piece of C code, and you can see that the C code there because I believe most of you have already forgot everything, so let's go over this again. So in the C code, you'll see we have two global variables. One is initialized, another one is not. And they have a name. And usually the developers, they will give a name to this variable. In this case, there are two arrays. And there is a function, the main function. Also, there is a name for that function, which is main. And there is an array of local variables. And so this part usually is on the stack. And there is a loop and assign a value to those two arrays. And we take a look at two machine code generated from the same C code, and we discover that they look actually totally different. And this is what we get from the Windows compiler. In this Windows compiler generated code, there is no function name, no variable name, no variable type, no variable size, and even the loop is not there. The loop was optimized by the compiler. And when we look at the Linux GCC version of this code, we saw that the assembly code was more faithful. It looks like this C code, but still, it's hard to recover the C code from the assembly code. So, but as a security analyst, usually we don't get this kind of C code. We only have the binary, and we need to understand what the malware is trying to do from this binary code. And this kind of binary code is still very simple. There is no protection. It is not trying to stop you from analyzing it. In real-world malware, there are a lot of layers of protections. Layers to stop you debugging it, layers to stop you to statically analyze it. And also, we did another analysis. We used a tool called PEID and IDAPRO to do kind of an actual Windows virus. So in this virus, we see that the entry point of the program, usually the entry point is before main. So main is not usually the entry point. The entry point is actually in the C library, and the C library will call your main function because when you are the developer, you develop the main function. The entry point is actually way before the main. But the entry point should be a code. But we see in that virus, the entry point is not in the code section, but in resource section. And which means usually the code part has been encrypted. And all the tools, they can only identify those are data and not code. That's why that's in the resource section, not in the code section. And also, when we use IDOT-Pro to open it, IDOT-Pro will use this blue color to denote code, and this is a whole process address space. So this is high address, this is low address. So since the high address here is blue, which means some code here, probably that is just some system error. And the developer's code usually will be somewhere here. And you can see we do not really see code here. That's because this part has been encrypted. It's not blue, it's just yellow. Probably here is a small stop here that is code, but it is all encrypted. So today we are going to continue our discussion in malware forensics with disassembly. But today we are going to do some real exercise, and we will go through all the details. So basically, assembly and disassembly, they are very similar things. And a disassembler is a tool that translates machine language into assembly. Because machine language is just bytes, and only CPU can understand it. We cannot understand it. So we need to translate that into assembly language. This seems very easy since there is a one-to-one mapping between machine code and the assembly language, right? Sounds like it's much easier than translating assembly language to C language. But actually, it's not that easy because at that level, when you are only looking at bytes, you don't know even where is the code. You don't even know the location if that is code. So that's why there are a lot of tools and a lot of algorithms to do so. And IDOT-Pro is one of the best. So basically, all the hackers, they use IDOT-Pro to try to crack those softwares. And this disassembler is different from assembler. So assembler is to translate assembly language into machine language. So usually, the developers, they can use assembly language, even though not many developers are still using assembly language. But if you are doing operating system programming, or you are doing embedded system programming, still you need to use a lot of assembly to make the program faster and to introduce less noise. Because to make the program more faithful, because we saw before, if you use C to program that, it's possible the compiler is not generating what you want. Even though the compiler believes they are equivalent, but it's not what you want. So sometimes you want to program in assembly directly. So for all the laptops, most of the laptops we are using Intel processor, and most desktops and servers we are using Intel processor. And the first Intel processor was called 4004. It was in the market 1970s, and you probably heard these two, AT&T and AT&T6. They are very famous and commercially popular processors. This is like one AT&T in 1970s. So that is a full functioning CPU. It's not very big. So, but even though Intel is still dominating the market, and all the phones we are using, usually we are using processors based on ARM technology. And it's getting more and more serious. ARM is even pushing that to the servers market. So those two are the major players in this market. And they use different technologies, they use different instruction set. So today, what we are going to look at is some malware running on Windows using Intel architecture, but the techniques we learned in this class, we should be able to apply to other platforms, ARM or RISC, and IDOT-Pro can support all kinds of processor architectures. So if you remember last time, the first time you open IDOT-Pro and load that image, IDOT-Pro was asking you what kind of architecture it is. So the instruction set all the Intel CPUs are using usually is called the x86 because it started with 86. Then Intel had the CPU 82, 86, and in the future a lot of other, but still we are using this x86 instruction set. So this instruction set has been there for 33 years. Obviously, it has changed a lot, and there are some specific processor architectures too, and the instruction set will change based with those new processor architecture. For example, one of the popular architecture we're using is called IA32, which means Intel architecture 32 bits. I think we talked about this before. Right now there are IA64, which means 64 bits. So one of the most important thing is x86 is a complex instruction set computer or complex instruction set. So you may have learned this from computer architecture class. Basically, there are two types of instruction set. One is called RISC, reduced instruction set. Another one is called complex. So basically, in a complex instruction set, there are so many instructions. In Intel architecture, there are more than 20,000 instructions. So the CPU can directly execute more than 20,000 instructions. So what is the benefit of it? So let's use this example. If you want to do some task, you can use fewer lines of assemblies. For example, we want to calculate we want to multiply two values together. And value 1 is in memory. Value 2 is also in memory. So what we can do is design an instruction for the multiply memory location 1 and memory location 2. Why this one is a very complicated instruction? Because CPU do not really have the ability to calculate on memory directly. Memory is an external device. So the CPU has to load the value from memory location 1 to some register. Register is part of the CPU. And also load the value from memory location 2 to the register, then multiply them together, probably in another register, then store them back to the memory. So even though this is one instruction, there are many steps. So this is called a complex instruction. The good thing about this is if you are a compiler developer or you are an assembly language developer, you only need to use this instruction. You don't need to use 3 more instructions. Load it into memory, load another one into memory, multiply them together, and store in the memory. So it's very easy for compiler developers and low-level language developers. So this kind of instruction looks like high-level language, looks like C language. However, there are also some disadvantages of this approach. First, it costs a lot of power. That's why RISC-based solutions, like ARM-based solutions, are more popular in mobile platforms because they save energy. Because to implement something like this, they have to use a lot of what is that called? Translators, some physical devices. So you have to put more physical devices on the CPU, and all of them are just consume power. So the other approach, which is popular, is, but by the way, this is just one example. This is just one example of how CISC can be designed. Even Intel architecture doesn't have an instruction access. The instruction you are going to see today in Intel architecture, you still need to do multiplication in register directly. But technically, it can be designed this way. This is kind of like an extreme case. So for RISC architecture, they only use very simple instructions. And usually those instructions, they can be executed within one clock cycle. So they break those complicated instructions down to simple instructions, and each of them will just consume the same time. So the benefit of it is this can be easily pipelined and can make it faster. And because there are only simple instructions, you don't need so many physical devices, and it will save a lot of power. For the austere, we use the multiply example. So in an ARM-based architecture, the program has to load the memory address to register A explicitly, then load the value of memory to B. Then this is like a product instruction. Then multiply them together and store it back. So obviously, the disadvantage here is this is just one instruction. So one instruction can be encoded in a 32-bit machine, probably just 32-bit. But here, in a 32-bit machine, we probably need 4 instructions. So which will make the program bigger. So the program might be bigger, and this one, the program will be much smaller, like 4 times. But no one is going to replace a lot of actually. So still we're going to have a closed architecture. For server side, probably we're going to use Intel architecture more, and for mobile, ARM is dominating. And 95% of the mobile and the IoT devices, or your iPhone, your Android phone, we're using ARM-based architecture.
Do you think AMD's sentence architecture is going to make a big impact?
Which one?
AMD's Zen architecture.
I don't really know that one.
It's pretty new. Came out like this month.
Is it based on x86 or it's totally?
It's totally new.
It's x86, based on x86.
Still based on x86. Yeah, that makes sense. Yeah. So actually, even x86 right now, they have a lower layer called I don't remember, microcode. They have a microcode layer. So microcode layer is kind of like a RISC architecture. Yes. So next, we're going to talk about the Intel architecture, because the exercise we're going to do based on Intel architecture. So first, there are many registers. So registers are just in-CPU storage. Usually they are very fast, but also very expensive. So usually they are implemented using SRAM or something even faster. And registers is the first level of computer memory architecture. So they are the fastest to access storage in your system. But usually there are not many registers. In Intel architecture, only probably 15, 16 general registers for you to use. So 16 times 32 bytes or 64 bytes, not many. And in the ARM architecture, there are more, probably 40 general registers. So if you want to do any logical operation or arithmetic operation, usually you need to put data in register. And there are some other control informations in some special registers. So here is a picture of the memory hierarchy in the current computer system. So registers, they are super fast. After that, we have L1 cache, usually L1 cache. So right now, we are in this multi-core system. So all the phones you're using, they do not only have one core, they have multiple cores, multiple computing devices. So usually L1 cache, level 1 cache, is inside each core. So each core has its own L1 cache. And several cores, they will share L2 cache. And in Intel architecture, there is also L3 cache. Usually they are getting bigger and bigger, so the registers only several hundred bytes. And L1 cache probably is also several hundred bytes. And L3 cache can be as big as 2 or 4 megabytes. And in our architecture, we don't really have L3 cache. We only have L1 and L2. And actually, we are doing some very interesting project to use the cache of side channel to send the information in the ARM architecture. It's a very cool project, but it's still undergoing. So after cache, we have memory. So memory is already not part of the CPU. And memory is also relatively fast, but it can be huge. Right now, we can have 16 or 32 gigabyte memory. And after that, we have hard disk. So this is the memory hierarchy. But hard disk is different from all the devices above because hard disk is persistent. You don't need power to maintain data in the hard disk. So I think several weeks ago I mentioned there is one kind of new device called the non-volatile memory, and this kind of memory is kind of between memory and hard disk. It is persistent, but much faster than hard disk. So that's why the boundary between them will be blurry in the future. Probably we will just use this in the future. So in this x86 architecture, we have these registers. So basically, this is the EAX is one register, and AX is just a part of EAX. So for example, EAX is 32 bits, and the lower 16 bits of EAX is named AX, and the higher 8 bit of AX is named AH, and the lower 8 bit of AX is named AL. So why do we have this? Because when Intel designed their first CPU, or the very early CPU like AT&T, it was 8 bit. They only have this part. Then they extended to 16 bit, 32 bit, and now 64 bit. But they want to, Intel and Microsoft, they had an alliance. They want to make sure all the programs written before can still be executed on newer platforms. That's why they are keeping those old names there. So those old programs generated by old compilers can still be executed on new machines. So basically there are AEX, EAX, EBX, so A, B, C, D, 4 general registers, and we have SP or ESP. Basically this is a stack pointer. So if you program in C, you know that all the functions, they have to use stack. And BP is the base pointer, or basically this is also for the stack. But I don't remember what B stands for here. And the DI and DS, they are used for indexing. So D is destination, S is source. Note that even though those registers, they have their own names, like C can stand for counter. So this BCS is usually used by compilers as a counter. But they are all general registers. They don't have to be used in a specific way. There are just some conventions to do that. There are other, this is called segment registers, just to denote where is your code, where is your data. And IP is the instruction pointer. It points to the next instruction to be executed. And E-flag are the flags, like overflow, carry, those kind of flags. So like I said, those the ABCD general registers, they do have names. A is called accumulator, B is called base, count, data. But this is more, now they are just, we have those names for us to remember them easily. Probably at the very beginning, like in the 70s, those registers are more used for those calculations. So if you want to do a mathematical calculation, you probably put that value in EAX. But now they are basically physically the same. So you can put the value in any of those general registers. And the index registers, SP stack pointer, BP, we talked about this. We were see some videos. Segment registers, special registers. You need to remember is IP. Is the instruction pointer points to the next instruction that processor is going to execute. So because of this, in many architectures, you cannot really directly change this EIP. So there is no instruction to move any value to EIP. There's no instruction to do that. So you can do a move. You can do a move a value to EAX, but you cannot move to EIP. But it doesn't mean you cannot manipulate that. There are a lot of tricks. People discovered a lot of tricks to manipulate that. So besides the registers, another thing we need to understand is the memory addressing mode. So basically, the address bus determines the amount of addressable memory. Like in the very early version of Intel architecture, 88 bits, only 8 bits, which means there can only be. So probably the memory. I think the memory, even though the registers were 8 bits, I think the memory addressing were 16 bits. But still, 16 bits is like 256 times 256 memory bytes in bytes. So in that time, how big is that? That's like by 4. It's something like a 5K or something. 64 KB memory. So that time, the physical memory can only be smaller than 64 KB because the CPU can only address 64 KB. So if you have a bigger physical memory, the CPU doesn't know it can exist there. So the amount of addressable memory is not really the amount of physical memory available in your system. The addressable memory is bigger than your physical memory. So like in our current 64-bit architecture, 2 powers 64, that's a huge addressable address. But usually we don't have physical memory that big. So there are many benefits of that. First, for security reasons, because the addressable space is huge, we can do a lot of randomization there. So it's harder for attackers to guess where it is, what they are looking for is actually. So there are 2 modes. One is called real mode, and another one is called protected mode. So basically, what we are using for all our desktops, laptops, we are using protected mode. But when it boots, the CPU boots in real mode for backward compatibility. So in protected mode, that is where we are going to use the memory management unit, MMU. So probably you started that in operating system class or computer architecture class. Okay, at the machine code level, we just have bytes. But when we use assembly language to program in the Intel architecture, or we disassemble machine code into disassembly, there are actually 2 different syntax. One is Intel syntax, another one is AT&T syntax, which is very weird because this whole thing is developed by Intel. Why we are not using Intel syntax? Probably because copyright issues before. So the major difference is, let's say we have an instruction move register 1, register 2. So which one is the source? Which one is the destination? So in Intel architecture, the destination is the first parameter. And in AT&T syntax, the source is the destination is the second parameter. That's a major difference. But obviously, at machine code level, they're the same thing. They're just when they translate into disassembly, they use 2 different syntax. So here is an example. In Intel, if you want to move source to destination, destination should be put here, source will be here, and AT&T is different. This is very complicated sometimes because as a security guy or as a hacker, you're going to use all of the tools, and sometimes you need to use IDAPRO. And when you use IDAPRO is using the Intel syntax. But sometimes it's Linux, and you want to Linux executable, and you want to use object dump or other Linux tools, and they all use the AT&T syntax. That's why I guess probably that's a copyright issue. Why all the Linux or using systems they are using AT&T syntax instead of Intel syntax. So you need to get familiar with both. At least you need to identify which syntax it is using. There are not major differences, just the destination and source. Today we're going to use IDAPRO, so we're just going to use the Intel syntax. So what kind of operations, what kind of instructions we should get familiar with? Because before we start the exercise, first is the move instruction. So basically the move instruction will copy content from one register to another. It can also copy the content of memory from a memory address to a register. It cannot directly copy memory value from one memory to another memory. It cannot do that because this is part of CPU. It has to move it to the register, then move it to another memory address. So there are techniques that can directly manipulate the memory, and you don't need a CPU to do that, and that is called a direct memory access, DMA. Okay, so instead of moving content from registers to registers, you can also copy a constant from constant to register. So if you see something like this, you can easily identify this as Intel architecture, because the other way doesn't make sense. You cannot move the value of EAX to 10. That makes sense. So this must be a Intel architecture, Intel syntax. And also there are different addressing modes. So for example, you can move, this is one instruction to move the value in a memory address to EAX. In this case, the memory address is 10. And you are not moving the number 10 in hex to EAX. You are moving the content located at the address 10 to EAX. And also you can use indirect addressing. So in this case, the register EBX is used as the address of memory. And you are not moving EBX to EAX. You are moving the content located at the address which is specified by EBX to EAX. And there can be indexing. You can, so something like this you can imagine would be very convenient for array operations. So ECS here can be a counter, and EBX can be the base of your array. Basically, you are moving the value of this array to one register. So probably you have a loop there, so that ECX can be incremented. So also there are in assembly you can use pointer to specify how big the data you want to move. In this case, you are moving to AL, so you can only move about 8 bits, 1 byte. So you can specify that I want to move 1 byte from this address to AL. So here is one example. Instruction move BL to AL. So basically, we're just moving 20 in hex from BL to 20 in hex to AL, which is part of EAX. And another instruction move 10 in hex to AL. So this is very simple. So all other registers will not be changed. Only this register will be changed, will be updated to 10. And this one, so this part is a memory. And this is a memory address. This is 10, 20, 21, 22, and this is a value and this memory address. So when we move, when we run this instruction, the value 12 in hex will be moved into AL, because this one specifies the address, not really the value. So obviously, in this case, we need to say what is in EBX first. In EBX is 20, so we are going to memory to look what is stored in this address, which is 34. Then 34 will be moved to EAX, and they can be added together. So basically, this is a move instruction. We are going to say this instruction a lot. And there are other instructions can move them up. For example, push and pop. There are two stack operations, and also there are instructions in the Intel architecture. So when you push something, you basically push the source onto the stack. But where is the stack? The stack is specified by the SP register or SP and BP. And you can pop and you can retrieve top of the stack to a register. And there is another instruction called the LEA, load effective address. And this instruction is usually used as move. So I already put those slides on Blackboard. So when we do the exercise today, you're probably need to refer to the slides. So when you say something like EAX like this, you will understand it's just a move EBX plus 10 to EAX. So we talked about the stack, basically push and pop, two instructions. We're going to say a lot. And for example, this is a SP, which is a stack pointer. Stack pointer points to this memory address. And usually in Intel architecture, the stack goes from high address to low address. So if we want to push something here, we want to push this value to the stack. So the ESP will be updated, and this value will be put here. So this is low address, this is high address. And this is a little endian architecture. So this one is no address, and this one is no address. So if we pop, then we'll update the ESP. So this part will not be used, and even though it is not deleted, it's still there, but we can, the programs can override it. They are obsolete. And other arithmetic and logic operations, we have add, addition, subtraction, logic and, exclusive OR, multiply, division, and shift. So all those instructions you are going to see today, if you don't understand the meaning, you can refer to the slides and also just do a simple Google that instruction and also our Intel assembly, something like that. So you can get what they are. And there are some conditional statements. These are very important. So you all program in C or Java, so you know what is condition. And in assembly, obviously, there are conditions too. And there are usually two instructions to test the conditions. One is called CMP, compare. So basically, it's a logic subtraction between arguments. So if we want to compare two values, obviously we have to put those two values in the register first. So we compare EAX and EBX. So after this, EBX, the value of EBX will be subtracted from EAX, and the flags, the E flag registers will be updated. So you can see if the 0 flags has been set. If the 0 flag has been set, which means those two are equal. Because after subtraction, the result is 0. So based on those testing instructions, we can have conditional jumps. So we have a jump E, which is jump equal. But in this case, if we have a compare EAX, EBX first, then we have a jump E there, and if the value are the same, then we will take that jump because they are equal. And there are other not equal, greater nets. So when you say something like this, just Google in our exercise. And also there are unconditional jumps. Basically, unconditional jump is the IP will just be updated. There will just be an absolute jump. There is no condition to be tested. I have several examples here. This is a C code. If A equals to this value, we will call this function. And basically, note that A is a variable in memory. So what we are doing in assembly is we compare the value A with the immediate number here. Then if the return is not 0, we will jump to here. If the result of this is 0, we will call this function. So if 0 means they are the same when we compare these two. So obviously, if there are multiple conditions like this, we just do it several times in assembly, equivalent. And if there is a while instruction, if there is a loop, so we were first, here is a compare. After the compare, we will jump back to the very beginning and jump to here. So that's the loop here. So every time we compare this, if they are not the same, if they are the same, we will jump back. So that is how a loop is implemented in assembly. And I have another example with the stacks. So this is a very simple function in C. This is a main function, returns an integer. And inside this function, we're not doing anything. We just allocate a local variable and return this local variable. So this is the assembly code of this whole function. First, we will push this EBP. So basically, because this function is called by many other functions, and we need to save the stack of all the previous functions. So we need to save the EBP. So if you don't understand this part, doesn't matter, because this is not directly related to what we're doing. But if you are doing security, all these are very important, because all the buffer overflow, the stack overflow, they are utilizing vulnerabilities in this part, basically. Vulnerability there? So we can, the second instruction is move the ESP to EBP. And also we will have a subtraction ESP. So by subtract the ESP, we can reserve some room for the variable lossing. In this case, the variable is an integer, 4 bytes. That's why we are subtract 4 here to reserve 4 bytes for this local variable. Then we can return things. When we return things in C, the return value is stored in EAX. That's why we say we first move 0 to this memory address. This is a memory address to memory. Then move that from that memory address to EAX. Then we can return. So the return value will be stored in EAX. So we talked about this multiple times. The beginning of the MDR, there are several lines of code, but we never have a chance to look at what those code are doing. So we're going to look at this. So who coded the MDR? Can you remember? Remember who gave the control CPU to MDR? What? I cannot hear.
The bootstrap.
Bootstrap. Yeah, basically the BIOS actually. So usually we're going to say the bootloader probably they are after the MDR. So it's a BIOS. At the very beginning when the CPU boots, it's the BIOS running, that's the BIOS where you give the control to MDR. You will load the MDR and give control to MDR. And the MDR's job is to load other VDRs and get control to them. Right? So let's see how it does this. So the first instruction here is CLI. It's a clear interrupt. Yeah. So which means the following code should not be interrupted by any external interrupt. So all the all the devices, hardware devices, they can generate an interrupt. Like your screen, your keyboard, they will generate an interrupt to request a service from the CPU and operating system. So the first thing in this layer, we just want to disable that. Then we will move this 1000 in hex to AX, then move it again to SS, and move this value to SP. This is like we are assigning a stack. Because if we want to use C programming, we have to assign stack. And the operating system, like a major part of the operating system is written in C. So when we jump to any, before we jump to any C code, we have to set up the stack. Then we move 0 to AX, and AX to DS, ES, which means we probably will not use it. We just put a 0 there. Then we put this number to SI. SI is a source index, and 600 to DI, which is a destination index. Then CX is 200. What is 200? 200 is 200 in hex is 512 in decimal. So that is, do you remember what that is?
This size of the number.
Yes, that's the size of the sector. So basically, so the CX is the counter. Then there is a repeat instruction, repeat move strings. So basically, this instruction will repeatedly move the bytes from source index to destination index. So what actually is moved here is the NVR code. So BIOS already loaded the NVR code to memory, and it's loaded as this instruction. It's hard-coded. Then the NVR wants to move itself, relocate itself to another memory location. That's what it is doing. It is copying all 512 bytes to another location. And after that, it has to do a technically jump to the next instruction, but the next instruction is not at the next address anymore. They have been moved. So that's why it's a far jump to another place. So after jump to there, it will check if everything is correct. And the interesting part of the NVR is this code. So there is one instruction called INT. So this is an interrupt. This is a software interrupt. So basically there are hardware interrupt generated by hardware and a software interrupt which is programmed in any program. So software interrupt is also called exceptions. In this case, this interrupt, what this interrupt can do is do a disk read. So it will read the sectors in the memory. So basically what this piece of code is doing is try to read the VBR into the memory and give the control. So basically it will read VBR to this address 7C00 in hex and give control back to that address. That's why it is moving itself. It is relocating itself because it wants to save that address to the next layer of bootloader or boot record. Does that make sense? Okay. So we have been talking about this several times. You see only probably 20, 30 lines of code. This is a very important part when our computers boot. Okay, so now we will start our exercise. We have two tasks in our exercise. Task 1, we just want to disassemble this NVR using IDAPRO. I already dumped the NVR, and we can, so you don't have to retrieve it from a disk. I put it on Blackboard. This one should be easy. We can finish this probably in 20 minutes. And then we will go to the next one. The next one will be more interesting. It will take probably 1.5 hours or longer, I guess. Okay. So let's do this one first.
our approach is better than prime approach.
What? It's better?
Yeah.
Why is that?
I will show you in the meeting.
Perfect.
Okay.
Yeah, that's good.